All right, good afternoon. A couple of minutes over time, but let's see. Okay, little bit of history for today. Today is November 7th, is the birthday for Marie Curie. Assuming everybody has at least heard of Marie Curie, if not read about her. I find a little bit of history fascinating. She is the first woman to be awarded a Nobel Prize in physics. And she is one of only 4 people worldwide who actually won more than one. So there's only 4 people in the entire history who have won 2 Nobel Prizes. So she is the only woman, she's the first and only woman to actually have won 2 prizes. And most impressively, it's in 2 different fields. So she won the first one in physics, and she won a second one a few years later in chemistry. The other one, the other 2 people, there's John Bardeen. He won, and he shared the first one with 2 other people, William Shockley and Walter Brattain. They were the ones who were the inventors or credited with the invention of the solid state transistor, which is something, again, I may have perhaps mentioned it, but it's something we'll look at in 315. And so he won the first one for that, and he won the second one for his work in chemistry. That was a few years later. So John Bardeen was working with Brattain and Shockley at the time in Bell Labs. And then shortly thereafter, they had a falling out. They each went their separate ways. And Bardeen went on to become a professor, I want to say at Illinois or Chicago. It's either UIUC or University of Chicago. I can't remember which one. Then he did some work in the field of further work in the field of physics and chemistry. And I think he won the prize in chemistry for his work in superconductivity. And another one is Linus Pauling. Yeah, Linus Pauling. He was a US chemist. He won the first one for his work in chemistry. Believe it or not, it wasn't that widely known that vitamin C is effective against the common cold. It was through his effort and his work that we all now know that vitamin C can be used to fight common cold. Anyway, and he won a second one a few years later. That was the Nobel Peace Prize for protesting against nuclear testing, right? And then the fourth person, Frederick Sanger, he won the first one in 1958 and the second one in 1980, more than 2 decades later. So his research was in DNA and genome sequencing, genomics, basically. So he won the prize in chemistry. Okay, he won the prize in chemistry. 2 different fields of science. Marie Curie is the only person who has won that. She's won in physics and the second one in chemistry. No one else. Anyway, a little bit of history that I find fascinating. Also, famously, it's known that she shared the prize, her first physics Nobel, with her husband and another French researcher. Right, so she was from Poland, and her husband was French, if I remember correctly. And so she was working in France at the time, and so then I guess they met and they married, and she took on his name. And so Pierre Curie and Marie Curie, and the third one was, it's a French name, so it's Bequeler, Bequueler or something. So these 3 people won the physics. They had a daughter. The daughter ended up winning a Nobel Prize. Daughter married someone, so there's a son-in-law, and the son-in-law also won a Nobel Prize. So, family of high achievers. Anyway, it's I don't know. I just find it very interesting and fascinating. Okay, let's get going with our topics. We are working with diodes. Today, we'll continue on with a couple more examples of diode circuits, meaning rectifying, clipping, and wave shaping circuits. And then we'll look at how we can use diodes to implement digital circuits or digital logics. So you all have taken 133, right? digital logic design, you work with binary number systems, zeros and ones. Those are just for us humans to design circuits. It makes it easy for us. But behind those numbers of zeros and ones, there's voltage and there's current, right? Classic example that I like to use is an analog switch. You have a analog switch, you know, like a light switch, for instance, to turn something on and off. You flip it. I mean, if it's off, circuit's broken. There's no current flowing through it. There might be voltage across it, but there's no current. I is equal to 0. And we can say that is logic 0. And you flip the switch on, circuit is connected, pathway for current to flow through, and we can treat it as logic high, right? Or 1. And so we'll use that to create logic gates, right? Behind logic design, there's actual circuits. And so we'll look at how we can implement those circuits using diodes. Okay, so we had finished this slide, and then I think I had assigned this for students to understand and implement. So at this point, I'd like to ask, how many of you tried it and got it or have questions? So let's get those questions answered. Yes. It, that is absolutely correct. That is absolutely correct. Because we are finding, excuse me, the Thevenin equivalent circuit, putting a resistor in parallel with our diode circuitry. So this resistor would be considered as series, right? It's going in there, so it's in series with that power supply. Okay, so that first resistor at the top is in series with the V-in voltage supply. That's a current limiting resistor. And the second one, this one, is in parallel with these 3 branches. So if I was to draw out this entire circuit in a way that might make sense, I would draw it like this. So I'd have a V-in. This V-in could be anything, right? It could be a DC source, it could be an AC source, it could be anything. And then I have this series limiting resistor. And the resistor in parallel. Oh. Then another source. And then we have this diode right here. And that's how it would be. This would be our V-in, the source. This is where we measure V out between these two. And then the rest of the circuitry is in parallel. So these 3 branches right here are in parallel with each other. Okay. The diode and the 5-volt source are in series. Okay. Does the circuit diagram make sense to everyone? Okay. All right. So we added another resistor to the front end, which has the exact same value as our series resistor. So let me just say series current limiting resistor. And then you have a resistor in parallel. Where have you seen this before? Just a few slides ago. Anyone have an idea? No. This was in the slides where we learned about voltage divider networks. One specific example was in the oscilloscope probe. In the oscilloscope probe, where we want to step down the voltage from a 10:1 ratio, if you recall, we had the series resistor 10 times the value of the parallel resistor. And so if it causes a voltage drop across both resistors, and so the oscilloscope probe can, let's say, if we supply 100 volts to the probe, it will drop 90 volts across the series resistor and only 10 volts across the parallel one. And so the oscilloscope only receives 10 volts. And then in the oscilloscope settings, we set it as 10x. The oscilloscope knows if it's measuring 10 volts multiplied by 10, and the actual answer is 100 volts. So that's the exact same principle that we're using here. The only difference is both resistors are the same value. So when you find the equivalent resistance for this one, RTH will be R divided by 2. Okay, so find the Thevenin equivalent circuit, as I pointed out in last class, and we need to convert this exactly the way we did the other one. And so let's it might not work. Let's see. And this would be RTH. So this becomes RTH, and this becomes VTH. And RTH in this case will simply be two resistors in parallel. So R in parallel R. So just 0.5 R, R by 2. How about VTH? Since both resistors are equal, what's the voltage drop across those terminals? Any guesses? No guesses? If it's R by 2, what is your best guess of the Thevenin voltage? Come on, is it that difficult? It's V in by 2. You're dividing the input voltage into two equal parts. That would be V in by 2. If you want any other ratio, then you refer to that voltage divider section, right? If you increase the series limiting resistor, then the parallel input VTH goes smaller. If the series limiting resistor is smaller, then VTH is larger. Let's take a pause, think over that. Let me know if you have any questions. Okay. And so from this point on, the analysis is exactly the same as the previous slide. In the previous slide, we had 5.7 volts and 0.7 volts for the diode voltage drop. Again, as a reminder, these three steps. So V in here was 5.7 volts. Your diode would turn on at 5.7 volts. And so V in must be less than 5.7. And so here, the operating range would double, and the answer would be, actually not here, let me just write it down here. The limits would be Vn less than 11.4 volts. And then for the other two diodes, because it's, sorry, not other two diodes, it's 0.7 volts that's required for the voltage drop. And so it would be 1.4 volts. Because at 1.4 volts will drop 0.7 across each resistor, right? Or 0.7 volts across each resistor. And so in reality, it just becomes this. Okay. So yeah, minus 1.4. Those are the two cases. Okay. So by applying a resistor in there, we have now effectively doubled the operating range of the circuit. Right? In the previous circuit, we could only apply 5.4, 5.7. Now we effectively have gone up to 11.4. Right? By applying a resistor to control it. And so that's how we can design circuits. By simply connecting resistors either in series or in parallel. All right, let's take a pause. Let me know if you have any questions. Yes. 0.5 times V in. Thank you. Okay. All right. Next, we come to a very common and very important circuit. Okay. Question simply asks you output voltage, but I'm going to, this is an important circuit as far as I'm concerned. Okay. It's the exact same circuit as the one that we saw previously. Okay. Diode and resistor are in series. There is no difference, except in that circuit, we took the output across the diode. In this circuit, we're taking the output across the resistor. The circuit is also known as a half-wave rectifier. A rectifier converts AC to DC. At the front end of any power supply or every single power supply that we use today, doesn't matter the instrument, whether it's a desktop computer, monitor, this projector, anything that any consumer device that you plug into a power outlet will have a power supply at the front end. And the first thing at the front end of every power supply is a diode rectifier circuit. Okay. Modern adapters for your chargers, like laptop chargers, mobile phone chargers, tablet chargers, what they have at the front end is exactly one single diode. So it's a half-wave rectifier that converts AC to DC. Because AC is a one-way device, so it converts AC to DC. Let's see how we can analyze this. Let's say we use ideal diode. So it's ideal diode in the positive half cycle. So this is the positive half cycle of the input of V in. The circuit can be modeled like this. what can we model the diode as? Is the cathode of the diode connected to any potential, either zero or voltage source? No. Is the anode connected? Okay. So the next step after that is to figure out what happens when the anode is higher than the cathode and when the anode is lower than the cathode. So positive half cycle, if the circuit reduces to this, you have the positive terminal of the voltage supply connected to the diode. So is the diode forward biased or reverse bias? The anode higher or lower? Because we are going up, it's positive. This is 0, positive half cycle. Anode will always be higher than the cathode because it's positive. So diode can be replaced as a short circuit. If diode is replaced with a short circuit, what is my V out? What is V out? V out is equal to V in. So it'll be an exact replica of the input cycle. This is only for the ideal diode, right? Only for the ideal diode. And then in the negative cycle, voltage goes negative. So this is the negative half cycle of V in. The circuit can be modeled like this. Now the anode is held at a lower potential than the cathode. And so diode is modeled as an open circuit. It's off and V out is equal to 0. Same circuit as the previous one, except we are taking the output across the resistor, not the diode. Okay. And so for ideal diode, V out would be exactly equal to V in during the positive and 0 in the negative. Now, the only difference in the ideal diode versus the CVD model is that in the positive half cycle, the diode is modeled as a constant voltage source of 0.7 volts. Okay. So V out will be V in minus 0.7. And that's the only difference. So if I was to plot the output, my output would be something like this. And then, sorry, let's draw it better. Straight line. Come on, come on, come on. There we go. All right. Of course, this is going to be exaggerated a bit. And the gap that we see between the two, that gap is 0.7. Okay, this 0.7 volts is required for the diode to turn on. Okay, so that's your V out of T. All right, let's take a pause. Let me know if you have any questions. So the question being asked is, what would happen if the diode is flipped? So sorry, I raised my thumb before you finished the question. So if the diode is flipped, would the V out would be V in plus 0.7? Not quite. If the diode was flipped, then the cathode would be held at a potential. And so instead of being a positive rectifier, it would be negative rectifier. So we would obtain the exact same waveform, but in the for the negative cycle, the positive cycle would be cut off. Okay. Yes. Current limiting. Just modeling output load resistance, perhaps, but current limiting. Yeah. Yes. Because negative half cycle, the diode is off. It behaves the exact same as this. CVD model and ideal diode model, opposite is exactly the same. No difference. It's going to remain off. And so negative cycle is clipped, V out is equal to 0. And yeah, positive half cycle requires 0.7 to turn on. Where? Sorry, where? In this one? Here? Okay, about this one. Diode is off. No output. Yeah, right here. 0. 0. So here's V out. V out equal to 0 volts. Even if the voltage drop across the resistor would be V in. Current flowing through there. So V out is equal to V in. Yep. All right, other questions? If V in is less than 0.7, output goes to 0. So the diode needs 0.7 to turn on. Okay. So let's say according to this would be 0.7 volts. Again, as I said, it's exaggerated, right? So the level of the waveform is 0.7 volts. As V in goes below 0.7, output goes to 0. Okay. That's how we arrive at the V out waveform. And then when it goes to the next cycle, it needs to climb above that 0.7 volts in order for it to turn on. Otherwise, V out remains 0 until then. And so here, it remains 0. Okay, until the intersection point. Okay, until then it remains 0. All right. Okay. One final important point. Sorry. What's the difference between these two circuits? Fundamental concept, 10 seconds to answer. They are the same. Emre says it's the same. Does anybody else? How are they different? The resistor changes the voltage. No, but what if they're the same value? Diode turns on. No, that's a good thought, but no. The answer is that there is no difference. It's exactly the same circuit. If you're a series connection, it doesn't matter where you connect it. Again, fundamental concepts, right? It's a series connection. We cannot slow down time enough that we can, once you flip the power source on, electrons are starting to move in the circuit. What we see is the combined cumulative effect of the resistor and the diode together, right? You turn the lights on, it's on automatically. Almost, not quite, but almost at the speed of light, if you will. So yes, the resistor does come first. If we slow down enough that it only takes a few seconds instead of like, nanoseconds or femtoseconds. But essentially, circuits are exactly the same. There's absolutely no difference. The point I want to make is this. In this circuit, the diode came first, the resistor came afterwards. We're taking the output across the resistor, right? So this circuit is this one. Diode comes first, you take the output across the resistor. And then the previous circuits we looked at, not this one, not this one. Yeah, this one, but without this one right here. And this one. So all these are all the same, right? Resistor came first, diode came next. Still, there's no difference in the circuit. The diode and the resistor are in series. The only thing we are changing is we are changing the output. We're changing the location of the output. We are changing where we are obtaining the output. Okay. So if you connect the circuit this way, your voltage transfer characteristics are going to look like this. You could apply a AC input voltage and you could still obtain a waveform similar to what we learned here. right? So both these circuits are the same. If you take the output across the diode versus the resistor, let me move this a bit. This is still a half wave rectifier. And this also is a half wave rectifier. No difference. In the other two circuits, we took the output across the diode, and so we can use this as a clipper. The half wave rectifier is also a clipper circuit, by the way, because it's clipping the negative half cycle. Okay, so clipper or limiter, the rectifier circuits, again, is also a clipping circuit. Sometimes these terms are used kind of like synonyms. Diode rectifying circuits, diode clipping circuits, diode limiting circuits. Okay, so again, there's no difference between the two. The only difference between the two circuits or the examples is the location of the output. The same circuit, but depending on what we want to use it for, we change the output location. Wow, I meant by yes. Good question. How is it changing AC to DC? Not quite. So there are a few other components that are required, and we will see that in 315. We have filter capacitors that give us a flat line, and then we add Zener diodes that give us, yeah. So a few other things that go in there. All right, next one. This page is simply a summary of how to apply the CVD model, right? And so that's for students. I just want to this is a continuation of the slide of the previous one. It's basically showing you how you're connecting the circuit, whether you have resistors first or the diodes first. You can change what kind of circuit it is. It just depends on your application, right? So this circuit is basically resistor first, diode next. And this circuit, it's diode first and resistor next. Okay, it is the exact same circuit, no difference. The only difference between the two circuits is the location of the output. All right, no difference. That's all it is. Okay. Fundamental concepts of pull up and pull down resistors. Okay. So in digital circuits, I don't know whether you have studied this before or not. Have you all come across the term pull up and pull down resistors? Some of you are saying yes, some of you are saying no. Okay. Okay. All right. So pull up resistor, as the name indicates, will pull up your whatever junction point. It pulls it up to a specific voltage level, and pull down almost always indicates it's pulling it down to 0 volts or ground, if you will. But purely stated, pull up means it is going to a positive value, and pull down means it's going either to 0 or negative value. Okay. So up is positive voltage, and down is 0 volts or negative voltage. In digital logic circuits, typically we just work between 0 and 5 volts. So not negative as much. Okay. And so the concept of these circuits is that there are switches And the switches, based on their state, whether they are on or off, will connect your outputs to a positive higher level, or it would connect it to a lower level. In digital logic circuits, higher levels are logic high or 1, and low levels or 0 volts is logic 0 or logic low, right? Binary number system. And so the fundamental premise, or operating principle of these circuits is that you have some voltage control switches, and based on the input voltages, the switches activate or deactivate as the case may be, and then your output is connected either to plus voltage, or it's connected to 0 volts. That's it. That's the fundamental premise of operation. Okay. And so in the pull-up resistor, you have your output terminal connected above the switch, right? So if the switch is closed, your output is connected directly to ground, right? And if it's open, then it's disconnected from ground, and now through the pull-up resistor, it's connected to the voltage source of 5 volts. And so you get logic 1 at the output. So on the left, if the switch is open, output is connected to plus 5 volts at the top. 5 volts I'm just using as an example, but logic high. So this would give us a high. This would give us a low. In terms of digital logic, this is a 0. This is a 1. All right. But now, if you take your output and place it below the switch, so your resistor is now connected directly, sorry, your output is connected directly to 0 volts or ground, then that resistor is pulling the output down towards 0. So if your switch is open, it gives you a 0. If your switch is closed, well, now your output is connected to plus 5 volts. And so it's a logic high or 1. So we have flipped the operation. Again, simply by changing where we're taking the output from. Okay. Let's take a pause. Let me know if you have any questions. Any questions? I well studied logic gates, and so you're all familiar with the 3 fundamental ones: and, not, okay, and nor, or, NAND, NOR, XOR, XNOR. Great. Was it all in 133? Okay, awesome. How many of you remembered? Well, actually, no, you haven't studied that, right? Implementing logic gates with circuits. Okay. Okay, great. All right, so let's look at that. Speaking of inverters, this is, of course, the voltage control switch, the CD4066. Okay. I just want to point out 2 things. It can operate at 5 volts and 10 volts. In the spec sheet, it's pointing out the resistance range. So if you operate at 5 volts, it can go, the operating resistance when it's on or off, it's 470 to 1000 ohms. And when it's 10 volts, it's 180 to 400 ohms. So wide variation, but it still works as a switch. Ideal switch, of course, it should be 0, but that's not possible. But the 4066 can go all the way up to like 18 volts. Okay. All right. This was, yep, this is the one. Okay, so you have a voltage control switch here. You have a pull up resistor because it's connected to the positive end of the power supply. So it's 10 volts. And then your output is taken between the resistor and the switch, right? So if the input A is low, if the input A is low, what happens to the switch? Open circuit. It's open. If it's open, if V out is directly connected to the plus 10 volts. And so this is logic high or 1. Conversely, if you, on the other hand, if you apply a high input to the 4066 switch, then it turns on. There's a pathway for current to flow through. And because there's a pathway for current to flow through, your V out is now pulled down to logic 0. Okay. However, this kind of switch has some resistance, which we just saw in the spec sheet, depending on the voltage that we're using, either 10 volts or 5 volts. Could be anywhere between 400 all the way to 1,000 ohms, which is pretty substantial resistance, right? And so R on is the on resistance of that switch, okay? On resistance of that switch. And so now, because it's on, it's going to create a voltage divider network along with this resistance. And then the output, we obtain 0.476, which would be considered low or 0. Okay. Again, concepts of voltage division. If the on resistance was smaller, the smaller it is, the smaller voltage we obtain at the output, right? So let's say your switch malfunctions, and instead of like on resistance of like 400 ohms, you end up, I don't know, like 4,000 ohms, let's say. Now your pull-up resistor is 10,000, and the on resistance of the switch is very nearly half of your pull-up resistor. So 10 volts will be split into 3 parts, and your output voltage will not be 0.4, it will be like 3.3 or greater than 3. If R on is approximately equal to 4,000 ohms. All right, and that's why the resistance of the switch matters. Okay, especially in these kind of simple logic circuits. Okay. All right, so we've gone a couple of minutes over time, but we'll end class here today, and we'll pick up here again on Monday. Quiz on Monday based on the material that we have covered this week. This was a 2-input NAND gate. This is a this is the logic inverter, of course. So is this the circuit that you all did in the lab? Something similar? Okay. Does it make a little bit more sense now? Okay. Because you apply one, you apply low, you obtain a high. So it's inverting the output. And you apply high, you obtain low. So again, inverting the output, hence logic inverter. Okay. All right. Have a good weekend.